This is by no means an authoritative overview of the history of EEG and MEG, but I hope that some pieces of information here will be interesting, if not useful. And I always find it intriguing that electricity for a long time was considered as a biological phenomenon, as something that comes from living organisms. For example, a few thousand years ago, the Egyptians already, apart probably from lightning, but a few thousand years ago, the Egyptians already knew about the electricity that some fish produced in the Nile. I guess this was some sort of catfish. And they even used them to cure or at least treat headaches. So I don't know how this worked or if it worked, but it was some early form of brain stimulation. And I guess people are more familiar with with static electricity. So if you rub an piece of amber, or in fact an air balloon on a woolen surface, a woolen jumper, then it develops the static electricity, and you can attract feathers or hair if you have some. And the old Greek word for amber is electron, and that's where the word electricity and in fact electroencephalography comes from. Then fast forwarding a bit, early science probably started with Galvani's experiments on frog legs. So he discovered, or somebody around him discovered, that they started twitching when lightning struck somewhere close by. So he then started to investigating that a bit more systematically, also in the laboratory with these machines that produce static electricity. And again, at that point, it was very much considered a biological phenomenon, electricity. It was very much to be considered something that is present in living organisms. And it was even used for more sinister purposes. So apparently, it was used for paying audience to experience dead corpses coming back to life. So it was applied to muscles, especially face muscles, to make them look alive again. And back then, apparently it was so frightening that at least one person, Mr. Pass, an unfortunate assistant of one of the surgeons who did this kind of stuff, was so alarmed that he died of fright soon after his return home. And I guess that happens when you think that, you're playing with the essence of life there, with electricity. It's somehow the energy that makes people alive. But we know a little bit more these days, even though, of course, it is the case that electricity is an essential part of how our nervous system works. And that was revealed more systematically in the course of the 1800s, when axons and neurons were discovered and the electrical properties were described. And for example, the speed of action potentials were measured in frog neurons. And as far as I can tell, the first ECOG from animals was recorded in 1875 in Liverpool by Richard Caton, invasively. Also around in the early 1900s, it was possible to measure brain potentials, I'm assuming invasively, but I'm actually not quite sure right now. And interestingly, this is basically resting state activation. So these days we are going back, or we have gone back to looking at the raw signals in our recordings. So this was how it all began. Of course, back then they couldn't store these data. They could just plot them. In this case, with artery pulsation and some other time markers on it. But it's I think interesting, that we are now actually going back to this type of data, of course, with more sophisticated methods. And EEG, as we know it, more or less, was invented in the 20s and 30s of last century. You needed big amplifiers in order to put a few of these electrodes on the head. And then the first phenomenon they discovered, or Hans Berger discovered, was the alpha rhythm, 10 hertz, a strong 10 hertz rhythm in the brain that you see when people get drowsy, close their eyes. It's often a nuisance for us, but of course it is an interesting research area in itself, still being investigated. And then a little bit later in the 60s, the kind of multi-channel EEG systems appeared as we use them today. People started plotting topographies and thinking about the sources of these generators. And I think shortly after that, the first dipoles were modeled on brain activity. It's also interesting that event-related potentials were, that we basically now take for granted. It's what we compute within seconds with our own data. It was only possible to compute them in the early 50s. So it was done for the first time at the Medical Research Council in London. And they didn't even use computers. They used some sort of contraption with capacitors on the rotating disk. And these capacitors were always charged a little bit more at a specific point in time following a stimulus presentation. I guess this was median nerve stimulation, something like that. And then afterwards, you could read the voltage out again at these particular capacitors representing different latencies. And that produced an evoked response or an event-related potential. So they went through all this effort just to see an average response. But that enables us now to actually look at event-related responses, not just the continuous ongoing brain response, but to brain responses to specific stimuli. MEG started also in the late 60s. First of all, researchers at MIT demonstrated that you could measure the magnetic field of the heart, and they used conventional technology, basically just a lot of copper wire wound up around into a coil, and they could show them that you can measure the signals from the heart. That got you into science in those days. Shortly after that, they could show that you could also measure brain responses with this kind of system. And in this case, they were also happy to just see the alpha rhythm, just like Hans Berger in the EEG. And they hypothesized that the signal comes from somewhere in the brain. So that was their idea of where the generators are. These days we look at these data, of course, with much more sophisticated methods, but these were the beginnings. These were the pioneers of MEG research. And this is the history of MEG, at least from the Helsinki perspective. So the NeuroMag and now MEGIN systems, they evolved from actually one-channel systems initially that had to be moved around if you wanted to have recordings from different locations of the head on the head. But then they started, from 4-7 channels over 24 channels. And then in the 90s, especially in the late 90s, they had multi-channel whole head systems, and the design is basically what we are still using today. The actual MEG sensors are arranged on microchips in a helmet-like fashion, and they have to be cooled down with liquid helium to superconducting temperatures because they are so-called SQUIDs, superconducting quantum interference devices. They are somewhere in this helmet, and there's a bit of electronics around, and it has to be in a magnetically shielded room because most things around us produce much larger magnetic fields than the brain. You can also wear an EEG cap when you're inside in the MEG system, so you can get both electric and magnetic signals at the same time, if you so wish. And this is the kind of system we have here at the CBU, for example. And there are some exciting developments going on at the moment in the MEG area. It would, of course, be nice if we didn't have to put somebody in a helmet like that. You can't really move in there. It's not the most comfortable way of experiencing an experiment. It would, of course, be much nicer if we could put these sensors as close as possible to the brain and arrange them in a way that our participants can also move around a little bit. And that is exactly what people are now doing. So these are so-called optically pumped magnetometers. They are not cooled down to superconducting temperatures. In fact, they're even heated up a little bit. So they can be used at room temperature. So you can arrange them on a cap like that, a bit with like EEG, or you can arrange them on a helmet like that. It looks scary, and I think there are now more comfortable options available. But the point is that you can move them as close as possible to the scalp and therefore as close as possible to the brain. It also means that you can move within certain limits. So in this case, the participant can drink a nice cup of tea or possibly coffee, even play ping pong, with herself in this case, but by now there are some systems available that also allow you to move around the room a little bit. But you still need a magnetically shielded room and a very well shielded room because these sensors only operate very close to zero magnetic field. So there really shouldn't be any external magnetic field around. So these systems therefore also need active shielding usually. So you can just about see it here on the wall, some sort of wires printed on the wall that produce a magnetic field that compensates for everything or the other magnetic fields that are around. Okay, this was my crash course in the history of EEG and MEG. And soon we will talk a bit more about analysis of these data. Thank you very much.